it's countering that motion, that movement, and that force is pushing against the movement. So it's slowing down the movement. That's deceleration. That's negative acceleration there. So we could also define the left. It could be going to the left, but the force would be countering that movement. It'd be going to the right then. I always assume that I'm moving to the right, unless anyone tells me different, because it just seems like that should be the positive direction and the left should be a negative direction. But that's completely arbitrary. You can define this left as positive if you want to, and this right as negative if you want to. That's totally fine. I don't really care. It's just you have to make sure that your sign conventions stay the same way throughout all of the class. So anyway, okay, it's moving, so I'm assuming that's moving to the right, but it's slowing due to friction. So it's got a force that is slowing it down. I'm going to use a different color for this. We used this kind of bright orange color for this. So I'm going to say, yes, that is slowing. That's a force in that direction. So if it was moving to the right, now it's slowing. But we can't, I want to underline this point here, we cannot show the velocity vector here because this is a free body diagram. It has nothing to do with the velocity vectors. It's only going to show you the force vectors. That's the only thing you draw on a free body diagram. So since you don't draw any of the velocity vectors, you just draw the forces acting on this body. So we know that if there's a force that's slowing this down due to friction, so I'm going to draw that little force due to friction right there. So overall, if you look at all the vectors added up, if you look at the sum of all the vectors, so that you look at the normal force plus the gravitational force plus the frictional force, these two, this is going to have, is a very simplistic kind of reasoning here, but I'm going to just try to walk through it right here. This normal force is pointing directly up with a certain magnitude. This gravitational force is pointing straight down with a certain magnitude that cancel each other out. So these two are going to be canceled out. And that leaves you with just this frictional force in this direction over here, which is when you add up all the forces, oops, I should have said, sorry, I need to make this more consistent. The sum of all the forces equals this, all these added together. So these two are, in a sense, canceled out because this vector points up and that one points down in the same magnitude but in an opposite direction. So the only force left over acting on this object that's moving it, that's changing its movement at all, is this frictional vector, this frictional force vector right here. So it's pointing this way, which means if it was moving to the right, now this force is acting on that movement, which is slowing it down to the point where it stops. And the point at which it stops, think about this, is there going to be any friction acting on this box when it stops? You should say no, because if there was a force due to friction, it would be moving the box in that direction, and that would be making it move. So as soon as it stops, that force due to friction is going to disappear. Okay, it'll probably go a little bit slower. There's definitely some relationship with how much mass there is in here, which we haven't gone through yet, but and the surface itself between this surface and that surface, but we haven't gone through that yet. That's to come, don't worry, it's exciting. Anyway, my main point here is that the only force that's really acting on this box, that's really changing its movement at all, is this frictional force. So it's in a negative direction here, so we could say that the sum of all the forces equals that negative, and we could even give this, if we wanted to, we could give this a value. We could say, oh, that's negative 1 Newton. So this whole thing would be negative 1 Newton. The sum of all the forces would be negative 1 newtons, which means that it would be, if we knew the mass of this, then we could figure out what the acceleration would be as well. Okay, so there is no, you might think that since this is moving that we need to somehow represent that movement with like a thrust vector. That's totally common that students say that, but it's not true, because if there was a thrust vector, that means that it would be moving, something in this box would have to be pushing out of the box to give it that thrust, like a rocket. If you have a rocket, it's hard to draw rockets that look like rockets. That's a rocket. Okay, rocket, now it's spewing out gas so it can be moved forward. So we can have a thrust vector right there. It's going to be slowed down due to friction. So we have friction working on it in the opposite direction. Okay, the air friction. Air is going to be pushing against it. It's going to be thrusting up. In space, it's really cool. In space, I'll just give you this little aside right here. I think it helps to illustrate the point of thrust. In space, where there is no air resistance, there is no friction, it's pretty cool. We've got these little ion engines. You should look this up. Where all you're doing is you're shooting out little tiny pieces of mass from your spaceship, just little tiny pieces. And that's just enough to accelerate this object forward because there is no air resistance. So just a little bit of shooting mass out the back and these little tiny ions is enough to propel the entire spacecraft forward. Here you have to shoot out massive amounts of gas and fuel, and it's not an explosion that is powering you so much forward, but rather that you're pushing things out of this that's pushing you up into the air. And here, there's nothing, you're not getting any thrust out of shooting something out the back. There's no rope that's attached to this box. It's just a box that's moving, and then it starts to slow down. And think about that. If you get this box that's moving and it's just slowing down, there's no additional force that's pushing this box. There is no thrust. It's just a box that's moving and then it's slowing down because this force is acting on it. The frictional force is acting on it, saying, hey, now slow down. And it slows and it stops. And at that point, there is no more frictional force that is pushing it anywhere. It's just sitting. And then we only have the situation where we have the normal force and the gravitational force. Okay, so I think I've explained this in a lot of detail and given you some examples. Some other things to think about. I like this one. There's one more box situation I want to show you. That's pretty cool. That illustrates this point. And most of you got this one right. So let's say that you've got a box. This is number 9 on your worksheet. Let's say you've got a box. There it is. And it's got a rope. It's just attached to, I guess, some stationary kind of object. And it says the object is motionless. So motionless. So when you see the word motionless or constant velocity, you should be thinking in your head, okay, this means that the sum of all the forces, so all the forces that are involved with this, they will add up to 0 because the object isn't moving, it's constant velocity. So all the forces will be 0 when you add them up together. So if you've got, let's see, if you've got gravity, gravity's going to be working on this, of course. So here's the center of the box. Gravity's going down. Great. What are the other forces? The other forces are the normal force. The normal force is always perpendicular to the surface that the object's on. So in this case, this is the surface that the object's on. So the normal force is going to be like this. But notice what's going on here. This is kind of cool. In this situation, if you add these two vectors up, let's try that. Let's add those two vectors up right now. If you add those two vectors up, they're not going to equal 0. So let's just say that, well, we can't really, we'll just do this visually. So we're going to say this is Fg, and then we're going to add Fn to it. Now we have Fn going here. So we've just added those two vectors. We started from here, and then we added them and they got to here. So right now, our overall resultant is right there. Whoops, should be straight. That is our resultant vector. So if that's a resultant vector, that if these were the only two forces acting on this object, that means that this object would have a force going down, like this, going down the slope. That's kind of cool. If we didn't have this little rope right here, then we'd have to have we'd have a force in this direction, an overall force going down the hill. And that's what you see when you go down the hill when you're skiing or snowboarding or whatever. So, what's the other force involved here to make sure that this object has is motionless so that this will equal 0? Well, we have another vector. And this vector is due to that string. So let's use purple. So if this string now is pulling in this direction on this box, it would have to be the exact opposite direction of this resultant so that it would get back to 0. So this must be what the tension force is. So I'll draw that right about like that. So if you add up all of these vectors, you add this green vector to the blue vector to the purple vector, green plus blue plus purple, they should come back to 0, to where you started from. And that's what we see right here. So this object is motionless because all the vectors added up together will get you 0. All right. We could say if the string was cut, for instance, let's just cut the string. I'm going to make this problem a little bit different. I'll say it has now, instead of being motionless, let's say the string now has constant velocity. Let's say, I'm sorry, this box has constant velocity. So now we won't have the force due to tension. But if it's in constant velocity, that means that there's no overall force pushing it and accelerating it down or slowing it down up this way. So if it's in constant velocity, all these they must equal 0. So instead of having this as being a tension force, now this would be a frictional force. And then overall, all the forces added up would still be 0. You just would have a constant velocity going downwards the hill, because the friction would stop it from accelerating anywhere down the hill. Okay, I hope that makes sense. If you need more explanation, please let me know. Okay, that's it for me. Good luck. Bye.